Hey, physicists. So glad that you are here to join us for week one of continuous learning. We are going to start this section with just some notes and a conversation. I do want to let you know that there is a note sheet, a PDF of it on Canvas. I tried to organize it as clearly as I could so that it would be fairly easy for you to follow along. So maybe before you watch all of the video, if you have a printer available and you can print out a copy of that, that might be a great way to follow along. If not, you can just use paper. Honestly, you can just listen, although I know that for me, it's easier to stay engaged when I'm kind of writing things down and keeping track of things. So I would encourage you to do that as you're working through this with us. Okay, so we're going to jump in and just give you a reminder of the things that we were talking about before spring break. So we were talking about waves, we were talking about sound waves and mechanical waves. And then if you did any of our optional things over the last couple of weeks, you know that we've started to talk about light. So today we're going to kind of focus in on light waves and what happens when they encounter a boundary. So all that a boundary is a medium change, a change between mediums. Just write that down so don't forget. Change between mediums or media. And that just a medium is just something that a wave moves through. Okay, so just like with any mechanical wave or sound wave, when a light wave encounters a boundary, a few different things can happen. We're going to focus on two of them today. So the first thing that could happen is that some of the light bounces back. And that's not a very technical term, so we're going to give it a more technical term, and that's one of the two big things we're focusing on today, and that is reflection. So if in addition to your pencil or pen, you have a highlighter, that would be one of the words that you definitely want to focus on, and that is the word reflection. So the game is, you've heard of reflection, you probably have a sense of what it means. So when light reflects or bounces back at the boundary, that means that the light is going to travel in the same medium. So I'm going to say the light travels in the same medium. So for example, if light is traveling through air and then it hits a piece of glass, the reflected light is the light that's coming back into the air. The speed of that wave is going to stay the same. And hopefully that kind of makes sense. Basically, the game is it's in the same medium. And just like it did with a sound wave, the medium kind of dictates what the speed is. If it's in the same medium, that means it's going to have the same speed. Okay. If we take a look at this next little piece here for the frequency, what happens to the frequency? Well, the frequency is going to stay the same. So I don't know if you remember, but we were sending a, a series of waves down, a periodic series of waves down that spring in the commons, right, again, before spring break. And if we sent one wave down every second, then that means that there would be a wave encountering the boundary every second. So the frequency with which it would bounce back would also be once a second or 1 hertz. Okay. Now, if we look at these three things, so we've got the speed, we've got the frequency, and we've got the wavelength. We know that there's a relationship between those three things, V, F, and lambda, okay? And we can solve this for lambda by saying that lambda is equal to V over F if we know that the speed stays the same and we know that the frequency stays the same and wavelength is velocity over frequency. Well, then by golly, you guys, the wavelength is also going to be the same. So in this little box here, it's not super exciting in terms of reflection. It gets a little bit more interesting when we start talking about the other alternative. And then we'll go down further on the notes in just a minute, but I want to kind of keep these two columns parallel here. So as we said, some of the light is going to bounce back into the same medium. That's the reflection. The alternative, the other thing that might happen is that some of that wave is going to be transmitted into the new medium. Okay. And again, that sounds a little bit fancy, but if we're going to give it a really fancy name, something sounding almost as fancy or maybe even more than reflection, we're going to call that refraction. So again, if in addition to your pencil, you've got a highlighter or your glitter pens, this is where you would want to get them out to mark the word refraction. So again, reflection is when the wave bounces back. Refraction is when the wave goes into the new medium. Hey, that's the next piece. It says what the light travels. Where does the light travel? Well, it travels into the new medium. Okay, so this would be light traveling through air into glass or into water or into whatever that new thing is. Okay, the speed, as we said here on the reflection part, we said same medium, same speed. Hey, we're in a new medium, kind of means that we're going to have a new speed. So the speed is going to change. And what causes that change, you ask? Well, the change is caused by a change in density. So it changes. I'm going to say due to a change or a difference. I'm going to say difference in density. Okay. Now, this isn't quite the same as the density that you talked about in chemistry, but it's similar, and it's similar enough that for our purposes, we're just going to call it density. There's actually this thing called optical density, which is what we really are paying attention to. But for now, we're just going to say that the higher the density, again, and it's not quite the same as the other density, but it's similar. Okay. The higher the density, the lower the speed of light in the medium. Make this a little bit bigger so my handwriting isn't quite as gross. I'm actually going to just fix that so that it's more legible. Lower the speed in the medium. Now, not only does that happen, but we actually can define exactly how fast light moves in any given medium. And the way that we do that, again, I mentioned that we talk about this thing called optical density. And the optical density determines a material's index of refraction. Oops, make that a little bit nicer here. Sorry. I haven't been writing on this thing for a while here. And hopefully you still have that highlighter nearby. That's another one of those things that I would highlight because that's another one of those terms that's pretty important. The index of refraction. Index of refraction is marked with the letter N, a little n, and n, the higher the index of refraction, whoa, that's not what I wanted. There we go. The higher the index of refraction, the slower the light moves. If you go on to take more physics classes, they'll define what index of refraction is. If we had had a normal year of physics, then we absolutely would have done the same. But for our purposes today, we're just going to leave it right there. Okay. So I just want you to be aware of that, to have heard that term, because we will use it later on in this lesson. Okay. So, oh, what's on that next column here? Well, it says frequency. So we need to think about, we know that the speed is going to change. The speed changes because of the different optical density, but the frequency, again, think about those pulses of wave that were going down the spring, right? If it hit that boundary once per second, well, it's going to be transmitted into the new material once per second. The frequency does not change. The frequency stays the same. I made this big box here and I want you to write this down because this is super important. Okay? The frequency of a wave does not change at a boundary. The frequency will always stay the same. Okay? Given that information and given what we know about wavelength, if we know that the speed changes, but the frequency does not, we know that the wavelength also is going to change. If the speed goes down, well, then we know that the wavelength of that wave is also going to go down. If the speed goes up, the wavelength is also going to go up because, again, the frequency stays the same. So that's kind of the basics of what we call those two things. But now we're going to look at three specific cases to see what kinds of things can happen when light actually hits that boundary. Okay, so three different boundaries that we're going to talk about. So here is case one. So this is on the same notes sheet. I just kind of divided it up for my organizational scheme here. Okay, so here we go. Case one. Let's talk about what case one is. Case one would be a flat boundary. Okay, and the wave is going to encounter the boundary, okay, perpendicular to the surface. Okay. So I'll draw some pictures about this in here in just a second, but really we're just talking about like a piece of glass or a like the top of of water in a cup or something like that, where it's just a flat surface. And again, we're talking about the wave hitting perpendicular or directly into that surface. The path of the wave um, for reflection, the wave is just going to bounce straight back. And if I was going to draw a picture of that, this is what it's going to look like, something like this. So I'm going to say that this is air up here, and this is, we'll say, glass. And just to kind of keep things consistent from what we talked about earlier, I'm also going to just tell you what the index of refraction is of these things. So the index of refraction of air is very nearly 1. And the index of refraction of glass is about 1.5. On the activity that you're going to work on after you watch this video, you get to use and kind of manipulate some things to look at those indices of refraction. So I thought just kind of throwing those in there would be helpful. To draw the wave or the ray diagram, this one's going to be very simple because it's just going to be one wave. So we're just going to have the wave, it's going to come straight in, and the wave is just drawn as the direction of the wave with the arrow, and then it's going to bounce straight back. Now, it wouldn't be very exciting if I drew it right on top, so I'm going to draw it kind of right next to it, but really they should be right on top of each other. It's going to bounce right back. Pretty unexciting. An example of this would be, think about while you're brushing your teeth and you're looking in the mirror, just like a nice flat mirror, right? That's what we're talking about. So we're just going to say looking into a mirror. While brushing teeth. You're just standing there, the light reflects off of your face, it bounces onto the mirror, and then comes right back. That's all we're talking about. Now, the path of the wave, when we get to a refraction situation, again, that's when it's going into the new medium. Well, the path of the wave in this case is also just going to be straight into the medium. Friends, this is not the most exciting case, just letting you know that, okay? It's gonna get better in just a second here. All right, but let's go ahead and draw this picture. So I'm gonna do the same thing that we did before. So here's air. Again, that's N of 1. And here is glass. So this is an N of 1.5. So again, because the index of refraction is higher, that means that the wave is moving slower, right? So this is opposite of how sound waves move. So light waves move the fastest that they can in a vacuum, and in air they move pretty close to the same speed. So this wave is going to come straight in, a nice little peak wave coming straight in. And not only am I going to draw that, but I'm also going to draw something to kind of represent the wavelength. So I'm just going to draw some lines here, some nice parallel lines. So these kind of represent, they call them wave fronts. Okay, and so these are just kind of like the crests of the wave, if you will. Now, once this wave moves into glass, well, it's just going to keep going. It's going to go straight into the medium, but as we know from what we saw earlier, we know that it's going to change speed, right? The index of refraction went up, which means that the light is going to move slower. And if the speed goes down, that means that the wavelength is going to go down, which in our case means that these lines are going to get closer together. So that means that these nice little parallel lines are going to get closer together. These are just kind of helpful to see so that you know kind of how fast it's going, because it's not going to cover as much distance in any given time. So that's kind of one way to think about what's happening in a refraction situation when we're just going straight into the medium. Another example that a lot of physics people use when we're talking about this, you can think about like if you're running straight in, you're on a beach, you're running really fast, and then you run into the water. You're running into a new medium, right? And even if you're running at the same pace, so you're putting your feet down at the same time, right? That's keeping the same constant frequency, your speed is going to be decreased because your step size is smaller, because it's just harder to make it to run through water than it is to run through air, right? Okay, so I'm just going to put that down here as an example just to kind of keep that in your mind, right? So running on a beach is a nice example. And then you, let's say, into water, okay, move slower, um, because your wavelength decreases because of that thicker medium, that thing that's harder to move through. Okay, so that's case one. Again, not the most exciting of cases. We're going to move on to case two. This is where it gets a little bit more interesting. So this is on the back of your notes sheet. Okay, we're going to start off for case two again with a flat boundary, but this time instead of just going straight in. Well, it's going to still be a straight line, but it's not going to be perpendicular this time. Now, the wave encounters the boundary at an angle. Okay? So, if we're going to have an angle, we might need to be able to define that angle so that we can actually measure it. So, the angles are measured from what we call the normal. Now, if you think way back into your physics experience this year, you've heard the word normal before, and maybe you even remember that the word normal means perpendicular, right? So we're going to measure it from this line that's perpendicular to the boundary. Okay, so if we draw a picture here, so I'm just going to kind of get this set up. This is going to be one medium. We'll maybe just pick air, and then maybe we'll have water down here. And we're not going to get into the reflection and refraction piece of it right now, but I just want to show you where that normal line is going to be drawn. So the normal, we said, is going to be perpendicular to the surface. I usually draw it just as a nice dotted line, okay? And then the incident wave, incident means coming in. Okay, I generally draw it. I try to, that was supposed to be a straight line. I apologize for the fact that it's not perfect. Okay, but that's my wave coming in, and my incident angle, the angle that's coming in, is always measured from that dotted line. So we mark this as theta. We know and love theta. Theta I is the incident or incoming angle. And then either for refraction or for reflection, we mark the second angle, theta r, as the, as we just said, reflected or refracted angle. And just to be clear here, when I'm saying incident or incoming, those really mean the same thing, whereas the reflected and refracted, it depends on the situation. So let's take a look. I'm not going to draw any other picture on that because it's going to be different for each of them, but we've got space right down here to do this. Okay. So before we jump in too far, I'm really sad that we don't get to be together for this because there's so many good demos, but I'm just going to show you a couple of quick things so that you can get a sense of what this might look like if we were together. So I'm going to try and click on this. Is it going to work? Oh, maybe not. Hold on just a second. All right, so we'll just take a quick look at this. And all I want you to watch right there is just that little piece. So if you look at that video, you can see that the light that's coming in from this black box, it's called a ray box, it goes in and it hits this mirror, which is just a different medium, and it's bouncing off. And as the person moves that mirror, you can see that the angle of incidence, or the angle it comes in, and the angle it comes out at both change. So just take a peek as he's moving that back and forth, okay? That's all I want you to see for that first part. So if we write down then what's happening for the light, we can say that it bounces back at an angle. Okay. Hey, well, what angle is it? Let's take a look. So we're going to go ahead and draw ourselves a little picture here. And I'm going to draw my normal. We're going to mark this one here now as, we'll do air, n equals 1. And we're going to use water for this example, mostly because the other example for refraction does use water. And we'll say that this is n equals, it's 1.33 for water. So the light is going to come in. So it's incoming like this. So that's my incident angle, theta I. And then we need to figure out what theta r is. So I'm going to go ahead and click here. Oh, there we go. So this is actually from the same video. And I'm just going to let them talk. It's pretty exciting, right? Are you guys excited about that? I know I am. Okay, that is not a coincidence. In fact, if you did that 500 times and you had an angle in, your angle out would be the same thing every single time. So we can go ahead and mark that. That's going to come out just like this. There's going to be your theta r. Okay, the game is that for a flat boundary, when the wave encounters a boundary at an angle, it will come out at the same angle that it goes in at. You may know this. This is called the law of reflection, and it is true. It always is true, and it works for when you're doing billiard balls hitting a wall. When anything bounces off, it always follows this law. So let's go ahead and write it down. It's called the law of reflection. One of the simplest equations that you're ever going to write down in my physics class. Yay, theta I equals theta r. That is it right there. And that is true regardless of the second medium. Always true. It's kind of crazy. All right. So that's reflection. Now we're going to move on to refraction. So this is where it gets interesting, you guys. So when the light hits this boundary, okay, what's going to happen is that the light is going to bend, okay, when it enters the new medium. And it might not surprise you that the amount that it's going to bend is going to depend on what the two media are. So this one, you guys, is one of my very, very favorite demos. And especially for my marching band friends, I'm so sorry that you don't get to see this demo. Someday I'll record it when I've got some marching band people to do this. And for those of you that don't like to march, then you're thankful that you didn't get nominated to do this. So this is a video that I found that kind of explains it in a similar way to the one that I do. It's more fun when you get to count off and actually step off, but we'll do what we can. All right, so let's go ahead and take a look at this video and see what he's going to say, and then we'll put it all together. Okay, so I've just totally cut him off. I didn't really mean to do that. But this is really what we saw in case one, right? As you can see, the wavelength or the distance between those rows gets smaller when they move into this medium where it's harder to march, where it's harder to move. So that's really case one. He's going to get to case two here in just a moment. Okay, so we're going to pause that right there and kind of put those pieces together, and then we'll come back to him because I want to find out what's going to happen the other way. But let's go ahead and do the real life example that the marching band kind of sets us up for. So let's take a look here. I'm going to go ahead and draw in this first little picture. I'm going to do air up here, and we'll do water down below. And then I'm going to go ahead and put my normal line in just like our friend on that video did, and also like we're supposed to. Okay, and then we're going to go ahead and draw um, our angle in. Now, the person on the video drew it coming in from the right. I almost always do it from the left. So I'm going to go ahead and do it from the left in this one as well. So the wave is coming in, it's coming in, it's coming in. That's, again, supposed to be a straight line. Sorry about that. And this is our angle of incidence. That's the angle at which the wave comes in, okay? And then just like the gentleman showed you in that video, when the wave hits this new medium, the medium in which it's moving slower, it bends. It bends because it can't move nearly as fast in that second medium. And so as a result, it's going to bend toward the normal. Okay. So that means that the angle of refraction, again, my straight lines are not very straight today. I apologize for that. You get the idea, hopefully. There, right there is my angle of refraction, okay? And that angle is going to be smaller because it's slowing down. So let's write down this in some words here. So the light moves from, it's a little bigger, less dense to more dense, okay? N1 or Ni is less than Nr, okay? And as a result, the wave moves slower. And as a result, the wave bends toward the normal theta I is greater than theta R. Okay, so that's case or like one example where we're going from more dense, or excuse me, from less dense to more dense, right? Where Ni is less than Nr. Let's take a look real quick at what the other situation might be. Okay, so I'm going to make this big again and we'll let his marching band go in the other direction. Oh, okay. We're not going to apply it right now. You'll get a chance to apply it later. Whoa, please stop. I have not, and I don't really intend to. Thank you, sir. Okay, so let's watch, or let's go ahead and draw the other situation. So in the other situation, just kind of for clarity's sake, I'm going to go ahead and draw the water up here and the air down here. So again, if I'm going to write my indices of refraction, because I feel like that'll be helpful, this is n equals 1.3. This is n equals 1. So we're going from a more dense medium, okay, something that's harder for light to move through, to a less dense medium, something that is easier for light to move through. Air has very, very few molecules in it, so it's easy for that light to move through it, right? It's kind of backwards from what we did with sound, because, you know, electromagnetic waves, light waves are just a little bit funny. Okay, so here's my normal line. Again, normal just means perpendicular, and I'm going to go ahead and draw in what's going on with my light. So I've got my incident, my angle of incidence, my incoming ray. Hey, that's the straightest ray I've drawn all day. Good for me. All right, and we'll call this theta I. And now we're going from something that is more optically dense to something that's less optically dense. It's easy for that light to move through the air. So once it crosses that boundary, now it's in air, it just can fly through it so fast, really fast, right? 3 times 10 to the 8th meters per second. It's going to be crazy fast. So it is going to be able to bend away from the normal, something like this. Okay. And we can mark this angle of refraction here, which happens to be then bigger than the angle of incidence. So let's go ahead and write down what we see here. So in this case, the light moves from a more dense medium to less dense. Okay, so I'm going to go ahead and mark those from more dense to less dense. And that means that Ni, the index of refraction of at the beginning, right, is greater than Nr. That means that the wave will move faster. That means that the wave bends away from the normal, okay? And that means that theta I will be less than theta R. All right, a little box around what we saw, what we did there too, okay? So again, if we had lots of time, you know, if we got to hang out together and do physics every day, then we would put some mathematics with this and really get into it. And there's some really great demos and some really great labs, but again, we don't have time for that this year, unfortunately. We just want to make sure that you've got the basics. So I'm just going to tell you the qualitative version. Remember, qualitative is not the number crunching version. This is just the concept version of this law, the physical law that dictates what happens in refraction situations. It has a special name. It's called Snell's law. And Snell is a physicist who I don't know any exciting things about. If you have time and want to look it up, let me know. I'd love to know something interesting about him, or I'm assuming it's a him. Um, but let me tell you the qualitative version. The qualitative version is that if the index of refraction of the initial medium is less than the index of refraction of the second medium, then theta I will be greater than theta R. And opposite of that, if Ni is greater than Nr, well, then theta I will be less than theta R. So that is just the concept basis for it. I want you to see that it's really true. I'm going to do one more quick video with you so that you can see how this works, and then we'll be good to go. Let me just show you this one because I think it's kind of a nice demo of what's going on here. Let's make it big. So let me explain to you what is going on here. So this is, again, one of those labs that I would love to have gotten to do with you, but we just don't have the time this year or the capability. Although we have a great activity for you that's very similar to this. So you'll get a chance to do it on your computer screen, which is awesome. So we've got this material here. I think this is glass. It's a semicircle of glass. We're shining light into it. Okay, so the ray that's coming in from the bottom is the incident ray. And then you can see, if you look very carefully, there's light that's going through that glass, and that light has bent at an angle, okay, and then it's coming out the other side. And so during this video, this gentleman is just literally reading data points, but you can see what happens as it goes, as it's happening. So I'm going to go ahead and let it play for a moment here so you can see what's going on. So they take that incident angle and they change it. So first of all, you can see that the angle of incidence, that 30 degrees that he just said, is not equal to the angle of refraction like we would expect it to be for the angle of reflection, but because now it's coming in at 30 and it's going out at 20, right? So the angle of incidence is greater than the angle of refraction. We'll watch it again, see what happens next. So he increased it by 5 degrees, and it didn't increase the angle of refraction by 5 degrees. It only increased it by just a couple. That's what we're going for. That's what you're going to see in the activity that you'll do as well. So I just wanted to kind of give you a picture of what was going on there. Okay. So friends, this is the big piece, the meat of what we wanted you to get today. I'm going to make a separate video for case 3. I love, love, love case 3, but it's really just an enrichment opportunity. The assessment that you will do is not based on it, but if you have an extra 5 or 10 minutes, I would strongly encourage you to watch it. Thank you guys so much for being engaged and being a part of our online learning. If you have questions, reach out to me or Mrs. Murphy and we'll help you out. Hopefully we'll see you on Monday for the Zoom meeting. And if not, that's totally fine. Reach out to us anytime. Take it easy, take care, and stay safe.